Actually, let me start by something that I've known Marcel. I had the pleasure of knowing Marcel Nicolet reasonably well, and if he would be alive today, I'm sure he would be very pleased that Bob is the recipient of the Nicolet Lecture. It gives me tremendous pleasure to introduce Bob Schunk as this year's Nicolet Lecturer. The 1 or 2 minute introductions that are usual for this type of occasion usually discuss the various scientific achievements and service activities of the recipient. I could tell you about the 300 plus papers, encyclopedia chapters, books, the committees Bob has served on, and so on, but I wanted to use my minute of glory up here a little bit differently. I want to talk to you a little bit about Bob the person that I've got to know over the years. I first met Bob when he came for a short postdoc appointment to Michigan in 1971. It was, I believe, his first crossing of not the Delaware, of the Hudson. It was the first time he crossed the Hudson to go into the wild, wild West. His Brooklyn accent, which he still proudly maintains today, his enormous enthusiasm was a great delight for us working with him. I can tell you that he immediately set out to educate me about transport equations, which, however, took me decades to understand and swallow. Eventually, he made a believer of me, and I think in a more serious vein, he set the community straight. The 4 years we spent writing our book very recently was another great educational experience for me. He taught this old dog new tricks. Talking about influence, his son Mike was born in Ann Arbor, Michigan, grew up in Utah, went to college in Boston, and yet he has a strong Brooklyn accent. Bob, how do you do it? Once Bob ventured across the Hudson, I thought he should travel further. It took me quite a few years to get him to cross the Atlantic. His first trip, his first overseas trip was with me that we took together to go to a yoga meeting in Edinburgh. Bob got sick within a couple of hours after arriving in Edinburgh, never left his hotel room, and went back home after that. However, that broke the ice, and now he is quite an intrepid world traveler. We all know Bob as a true theoretician of the highest order, but I'll let you in on a few secrets. Bob drives a truck, pumps iron, does his own repairs on the complex swimming pool machinery that he has. I've actually seen him on skis, and he's a wild, wild man on snowmobiles, venturing yearly to the middle of Yellowstone National Park. He's certainly not the mild, impractical scientist we all know and respect. On a personal note, Bob is a good friend with a wonderful, quirky sense of humor. Our association has been intellectually highly beneficial and personally enriching. So with this very brief introduction, I will sit down, shut up, which is difficult for me, and let Bob take the floor and talk about his chosen topic, aeronomy, from exploration to data assimilation. Bob?
I want to thank Dan Baker and Andy Nagy. And I guess you can see Andy Nagy has been a close friend for a long time, and I'm starting to realize he knows too much about me. So probably we have to keep our distance a little bit, Andy. Andy is also, has been one of my mentors over the years and has given me a lot of advice that's proven to be extremely valuable. Of course, when Andy gives you advice, the first thing you do is ignore it and get irritated with him. But then the next day you sort of think about it, and typically he's right 90% of the time. And he'll let you know that his track record is 90% of the time as well. Now, for this lecture, what I decided to do, since it's supposed to be a general audience, I decided to stand back from aeronomy and try to look at the big picture. Where has aeronomy come from? Where is it now? Where might it be headed? But of course, I can't cover the whole field, so I have to focus on a certain thing, and I'm going to focus on data assimilation. So the one thing I noticed in sort of looking at the big picture of aeronomy was that if you look at progress in aeronomy, it sort of came in jumps. We always have a small continuous rate of progress, but then all of a sudden you get a quantum leap in progress. And, ooh, this is powerful. Hope I don't burn the screen up. But at any rate, we had advances in aeronomy that were significant because of an important discovery. Perhaps it was a new instrument that was developed that was important, the advance in computer power, or a new scientific program. And so the question I raised is, are we ready for another advance in aeronomy? And I mean a significant advance, not a small one. So what I'm going to do in this presentation, I'm going to give a brief tutorial on aeronomy. I'm going to show you that there's climatology and there's weather, and it's highly variable. Just in case you're not an expert on the field, you at least get a feel for what's going on. Then I'm going to give a brief history of some of the important steps in aeronomy. I'm going to talk about the current status, but I'm going to do it from the data assimilation point of view. So I'll talk about what issues are important for data assimilation, and that includes physics-based models, data assimilation techniques, computers, and data sources. And I'm going to wind up with indicating that physics-based common filter data assimilation is an important step forward in aeronomy, and it's quite possible that if it proceeds as I think it will, it could lead to another major advance in aeronomy, and that's the theme of the presentation. Now, first of all, to get to the tutorial, for those of you not familiar with the ionosphere, there's a D region, an E region, an F1, and an F2. We got a top side, but at low altitudes in the E region, essentially have molecular ions are the dominant species, NO+, O2+, and N2+, and chemistry dominates at that altitude, although transport processes cannot be neglected. As you go up in altitude, the main ion is O+, and it also leads to the peak density in the ionosphere. The peak density, the maximum density, is an O+ peak, and it's around 300 kilometers, but it could vary markedly. And it varies anywhere from 10 cubed to 10, something times 10 to the 6, depending on where you are on the globe. As you go up further in altitude, H+ becomes the dominant ion. And because this is a Nicolet lecture, I felt obliged to put a few chemical reactions on the board. So the F region is pretty simple, so I started there. You have neutral atomic oxygen, it's photoionized, and you get O+, and then O+ interacts with the molecules N2 and O2. And it's lost, and that's the main chemistry that occurs in the F region. But unfortunately, transport processes, or I should say for my career, fortunately, transport processes are important along the field lines, and electric fields are important, and neutral winds are important, so things are more complicated. As you go up in altitude, there's one chemical reaction really that's important, and that's O+ interacting with H to give H+, and then the reverse reaction. So those are the main chemical reactions that we need to worry about. Now, if you look at the near-Earth environment, things are much more complicated, and I want to look first at high latitudes. These are the magnetic field lines of the Earth in the near-Earth environment. And at high latitudes, the field lines can stretch deep into the magnetotail, well past the orbit of the Moon, so light ions can flow up and out the topside ionosphere and escape the ionosphere. But the plasma also convects horizontally across the polar region due to magnetospheric electric fields, so you got flow this way. And if we take a look at that first and then come back, so if we look down on the polar cap now, so for example, if we go back there, it'd be good if I pressed the right computer. If we look back here, suppose we're standing up here and we're looking down on the polar cap, what do we see for this anti-sunward convection? Okay, that's what we want to look at. Well, here we're now looking down. This is the magnetic pole. This is magnetic latitude and magnetic local time. This is noon, dusk, midnight, and dawn. And the magnetosphere is trying to get the plasma to flow in an E cross B direction across the polar cap, anti-sunward. And this is the terminator for this example. So it's anti-sunward, but the Earth is co-rotating. I mean, the Earth rotates around, and there's a co-rotational electric field, and it's trying to get the plasma to co-rotate. So at mid-latitude, you get co-rotation. At high latitude, you get convection due to magnetospheric electric fields. And then, of course, the vector addition of both processes is the end result. So again, anti-sunward flow over the polar cap, return flow at lower latitudes. And this produces what I call high-latitude climatology. There are certain features that appear that are distinct. And so if we look here, the plasma is coming from the day side. This is the terminator. So this is sunlit. The densities are high. And the plasma then convects across the polar cap. If the convection is slow and you get in darkness, the plasma decays, and you can get a polar hole appear right before the auroral oval. And in the oval, you get enhanced ionization, you get production of plasma. So you get a density increase. On the other hand, if the convection is strong, it could bring the high-density plasma across the polar cap, and you can get a tongue of ionization in the polar cap. And of course, you have, as I said, high density throughout the oval due to particle precipitation. But equatorward of the oval on the night side, the plasma E-cross-B drifts into this region. Over here, it's trying to co-rotate and it's going back. You got plasma from the magnetosphere being forced this way, co-rotation this way, and you get a cancellation of the two processes. So you get a low speed or stagnation region here, and it's in darkness, and you get deep densities. The peak density in F region could drop down to 10 cube per cubic centimeter. And that tends to then slowly drift around the night side, and you get this main trough. So you get certain features that can be recognized orbit after orbit or day after day. However, things vary. The electric fields vary, the neutral wind varies, and the terminator moves. So if you look at the variation, then you have what's known as weather. And this is a plot of F0, F2, the critical frequency, which is related to the square root of electron density. And this is a digiSonde at Kanak in Greenland, and it's making a measurement every 5 minutes. So this is the critical frequency in megahertz versus time from 0 to 24 hours. So you're sitting at that digiSonde, well, a graduate student sitting at the digiSonde making measurements every 5 minutes. And every 5 minutes they make a dot, and you do it for 3 days in a row, January 17th, 18th, and 19th, and this is the scatter you get. So just routine measurements, and you can see that, you know, there's a lot of weather processes taking place. Now, if we go to lower latitudes, of course, there are weather features at mid-latitudes. I'll just show one more at low latitudes. At low latitudes, the magnetic field lines are horizontal, parallel to the Earth's surface, and there are dynamoelectric fields that during the day point to the east, so the E-cross-B drift is upward. So the plasma drifts up across B field lines and then slowly diffuses down, and this is called the equatorial fountain. And that'll have an impact on the densities, and I want to show that. Here, the B field is horizontal, the plasma is drifting. This is a snapshot of the density as a function of altitude and magnetic latitude. This is the magnetic equator, and it's color-coded with red densities being high and blue low. And the plasma E-cross-B drifts up, and then it slowly diffuses down along field lines. And the net effect is you get the Appleton anomaly or the equatorial anomaly, where you get density bulges on both sides of the magnetic equator. And the fact that they're asymmetric is due to the fact that you got a wind blowing across the equator from the southern hemisphere in this particular simulation to the northern hemisphere. And this is a simulation that was done with Dave Anderson's equatorial model. However, again, if you just look at the density profiles near the magnetic equator, you find out that they vary markedly from hour to hour and from day to day. And this is GPS met satellite data, and it's altitude profiles determined from occultation. And you can see during the day there's quite a bit of scatter in the density profiles at the magnetic equator. And this is daytime, noon to 1400. At night, the scatter is even greater. So you're talking about more than factors of 10 change in the density. And again, this is weather. So that was just a brief tutorial on the ionosphere to give you a feel that we have certain features that reappear all the time, and then superimposed on that is a large variability. So now what I like to do is sort of go back and look at aeronomy. Where have we come from? Where are we now? Where might we be headed? I shouldn't say beheaded. Where might we be going? And so I just sort of, you know, you can tell you're getting old when history starts to become pleasing to you. You know what I mean? So I looked at 1901, and, you know, Marconi transmitted radio signals across the Atlantic, and that was proof that there was a conducting layer in the upper atmosphere. Actually, Forrest and Fuller were the first ones to determine the height of the conducting layer, but they were not scientists. They worked in San Francisco for the telegraph company, and they used the telegraph lines to deduce the height. So, of course, the scientific organizations didn't accept that, and it wasn't until 12 years later when the official height was determined. And then the ionosphere, the word ionosphere was coined in 1926 by Watson Watt. Sidney Chapman did his famous work in 1931 on photochemical equilibrium. He assumed that you just have photoionization of O+ and recombination with the moleculars N2 and O2. Of course, Nicolet began his work in 1938 on the D region ozone in the mesosphere, and people indicate that he virtually invented the D region. It was only in 1946 that diffusion was determined to be important. And I shouldn't mention it, that was 3 years after I was born. So I was pleased. I was celebrating my 3rd birthday with that result. And then we have 1946, the first V2 was launched from White Sands. The first book on the ionosphere was published by Carl Rava in 1952. And of course, the big event, Sputnik, 1957. And then the Van Allen radiation belts, 1958. And typically I ask that question to my classes, to my students, to see which ones are good. Who invented the Van Allen, who discovered the Van Allen radiation belts? And they get it right 50% of the time. Now, what I wanted to do was I wanted to look at where significant progress was made in aeronomy, a major step forward. And clearly the preeminent program was the International Geophysical Year, in my mind. So this is sort of a biased presentation. But at any rate, this was important. And there were 120 ionospheric sounders around the globe at the high latitude domains. And after I produced these view graphs, I realized there were another 60 at mid and low latitudes I missed. So there was a total of 180, 50 VHF emission and Whistler stations, 180 geomagnetic stations, 60 auroral stations, 30 cosmic ray stations. And then, of course, you have Sputnik and satellites and rockets. So it was truly an amazing program. And I can't go into a lot of detail, but I just want to show you the 120 high and mid latitude, the high latitude stations for ionospheric sounders, ionosondes. And the important thing is they put some of these on ice, not on land, just so they can get better geographical distribution. And there's another 60 here that I missed, that Jim Whalen provided a figure for me, but I already had too many figures. But at any rate, the beauty about this was they operated continuously for a full year at 15-minute intervals. And on the world days, they operated at 5-minute intervals. And a lot of exciting science came out of this. And in fact, the data are still being used today. Jim Whalen has a series of nice papers using the IGY data. Now, an instrument that allowed for a major advance in aeronomy, in my opinion, was the Incoherent scatter radar. The Incoherent scatters radars in general, and I'm showing the Arecibo one because in 1971 I spent a month working with Herb Carlson at Arecibo, so this is my total extent of experimental work in my career, so I thought I had to show this. But this is a very impressive facility. But the incoherent scatter radars can provide altitude profiles of the electron density, the composition, the ion electron temperatures, and you can also deduce the neutral gas parameters, so that's important also. So I view the incoherent scatter radar as an instrument that came along that was significant. And of course, they quickly, once you build one, you don't stop. Okay, so they developed a chain of incoherent scatter radars starting at Jicamarca in Peru, and then Arecibo, Millstone Hill, and then Sonderstrom. And this chain was important because it allowed you to track the flow of energy and momentum and mass from high latitudes to low latitudes during geomagnetic storms and substorms. So this was significant. Of course, images, satellite images, and satellite data in general, but in particular, satellite images are really crucial. And this is just a picture of the aurora from the ground. That's, you can tell you're on the ground because of these trees. That's how I know it's the ground at any rate. And then from space, you really get to see the spatial structure of the aurora, which is valuable. And you could watch it as a function of time. And when I first saw the aurora early in my career and I saw it moving around in the sky, I thought there's no way you can do steady-state models of this. So my advisor at the time was doing a steady-state model of the aurora. Now, if you're a theorist, there's another major advance made, and there's only 10% of the community is theorists, and so only 10% will agree with my statement. But supercomputers came along, and they were very important. And this is the CRAY IA. It's the first supercomputer I operated on, and it was 1997. This was an 80 megahertz machine. But the advantage of computing, I know, it was 80 megahertz, and it was a high-speed supercomputer. We were all excited to use it. And the advantage of the supercomputers was it was the first time that theorists could actually develop global models that were semi-realistic. Okay, so that's why I viewed that as an advance. So now what I want to do is, that was just a brief history with me pointing out a few things that I felt led to advances in the field. But now what I want to do is look at where might we be going. So first I'll talk about the current status, but there's so many topics I could talk about. I just want to focus on getting to data assimilation. So there are 4 issues that are relevant to data assimilation. One is physics-based models. You need a physics-based model to do data assimilation properly. You need assimilation techniques. You got to worry about whether the computers can handle it. And of course, data sources. This is the critical one. You need a lot of data. So I will address these 4 issues next. Now, physics-based models. The question is, are there sophisticated physics-based models that we can use for data assimilation? And you don't even have to read this. Just look at the whole view graph is filled. So the answer is yes, there are physics-based models. We've got separate standalone models that are global for all the regions, the ionosphere, thermosphere, plasmasphere, polar wind, magnetosphere. Of course, we've got every coupled model that you can think of here, ionosphere, thermosphere, plasmasphere, and so on. And now at NCAR, they're already going all the way, they want to go from the sun all the way down to the Earth, to the surface of the Earth. So, the answer is yes, we have physics-based models that are sophisticated, that can be used in a data assimilation scheme. And this is just an example from some of the work we did that, here's evidence of the magnetosphere, and here's the polar wind, and you could model that simultaneously with what's going on in the ionosphere, and simultaneously with what's going on in the atmosphere. I don't want to get lost in the details of the science, but you can, this is just a snapshot across the polar cap, and as a function of altitude, of the O+ density. And you can see this upstreaming of O+. And simultaneously, you can get propagating holes in the Earth's upper atmosphere and the thermosphere. So they're not only do we have sophisticated models, they're high resolution, and you could run them down with any time constant you want. The next topic is, if you have physics-based models for data assimilation, do you have rigorous mathematical approaches to assimilate the data? Okay, that's the next topic. And the answer is yes. There are a lot of rigorous mathematical approaches. The meteorologists have been using them for 50 years, the oceanographers for 20 years, and one of the most popular ones, or perhaps the most famous, is a Kalman filter. And I decided not to give the equations for the Kalman filter. They look pretty simple. They're matrix equations, but I decided not to show them because whenever I show equations, I notice all the experimentalists in the audience start to get nauseous. So I avoided that. And I turned it into words. A Kalman filter is a powerful way of assimilating data into a time-dependent physics-based model. It performs a recursive least squares inversion of all the data for the electron density using the physics-based model as a constraint. You don't just do a least squares fit. You've got to do it within the physics of the model. It's been proven mathematically to have the least expected error given the measurements, the model, and the error statistics. So in other words, if you have a physics-based model, you have to know the model characteristics as well as the uncertainty in the model. You can't assume the model is perfect. For every data type, you have to have not only the data, but the uncertainty in the data. And what the Kalman filter does is take into account the uncertainties in everything and combines it in an optimal way to propagate the state. And the state is the ionospheric density for the simple case that I'm talking about. Now the next question is, do we have high-speed computers to handle data assimilation? Now of course, certainly at the supercomputer centers, we all know they're up to gigaflops, okay, floating point operations per second. But if you're developing a data assimilation model, and it's going to take 5 years, because that's the length of funding you have, it always works out that at the end of the funding, the model's done. You want to do it at your home institution. It's really difficult if you don't have a supercomputer close by to develop these models. So you want to look at it, can you develop them at your own institution? And the answer is yes, you can. You can have homemade computer clusters. You can have Beowulf clusters that some of you may be familiar with. Or you could just string some PCs together yourself and put a cluster together. And so what I did here is just show, this is Intel Pentium chip. And this is the speed in megahertz versus years going from 1970 to 2010. And you can see that the speed of these chips have increased linearly. And in the last 6 years, we've had a 10-fold increase in the speed of the computers. And we went from 100 megahertz to 1 gigahertz. And I just saw advertised on television, it's over now 3 gigahertz, the chips are. So the speed of the computers increases rapidly, and every 6 months we buy a new chip, a new computer, so we can get more speed. And you can put clusters together, and I should point out that I'm going to show some results from some data assimilation work that we did. And we did it with a network of 24 CPUs. And the whole system costs like $25,000. So we're not talking about a lot of money to put a cluster together that can handle data assimilation. So certainly you can do it at an institute. Now this is the biggest question, and I saved the last of the four. Do we have a lot of data available to do data assimilation? Now that's what's really handicapped the field in the past. You know, we were data starved. And what I want to show, or at least can try to convince you of, and I'll do this pretty quickly by going through a lot of view graphs, that in aeronomy we're no longer data starved. And during the next decade there'll be more and more data coming online that really makes it viable to do a data assimilation model. So there's different data types, and you know, you can get ionosons, you get bottom side electron density profiles from the ionosons. In situ DMSP satellites or any other satellite can give you the measurements of the electron density along the satellite track. You got ground-based GPS receivers linked to the GPS satellites, and you can get total electron content along those links. So in other words, you just add up all the electrons along the link, so you can get that. And of course, you're going to have radio beacons. Paul Bernhardt puts radio beacons on low Earth orbiting satellites, and you can do tomography. And pretty soon the cosmic satellites will be launched by Taiwan, and you'll be able to get occultation between a low altitude satellite and a high altitude. And you can not only get total electron content along here, but as the satellite comes above the horizon, you can get altitude profiles. And then there are going to be some UV images coming on board in the coming years, so you can get UV images on the limb and in the nadir direction. So this is just the type of data, but I'm going to now go through a bunch of view graphs to show you how many data sources are out there. This is Japan, and it's the GPS receivers of the Earth Observation Network in Japan. They're dual frequency receivers, so they're high quality. You get 1,000 receivers throughout Japan, and the mean separation between the receivers is 25 kilometers. So that's a good spatial resolution. They get 5,000 satellite receiver pass every 30 seconds, and what they get is a slant total electron content between a receiver and a GPS satellite. You get the slant total electron content. They get 5,000 TEC values every 30 seconds, 12 million per day. You need at least 2 graduate students to handle that. So, you know, in Japan alone, we're getting 12 million data points. If we look in the United States, this is the NOAA CORS network. I forget what the acronym means, but it's not really too important. Currently, there are 332 sites, GPS receivers on the ground in this NOAA network. And again, you get slant TEC between each one of these sites and the GPS satellites. And typically, a given site can see more than one GPS satellite. It can look in different directions to different satellites. And I should point out, we already have developed a Kalman filter data assimilation model that automatically assimilates data from all 332 sites. So a model that does this already exists. And it's a regional model over the US. Now, of course, we have a worldwide ionoson network, and there are over 100 ionosons throughout the world that are providing data. Then there's an official global GPS network, and there are 100 sites in this official one, and the data come into JPL. And this is just a diagram from their webpage that shows where these 100 sites are. And the circles show, if you go down to an elevation of 10 degrees, what your range of view is, if you go down to 10 degrees elevation. But there are over 100 sites there. The cosmic satellites will be launched. They're going to be low Earth orbiting satellites. There'll be 6 of them. I think they keep delaying the launch, but I think it's within 2 to 3 years. And you can get occultation between the cosmic satellite and the GPS satellites. There are 24 GPS satellites. And you can get occultation between cosmic satellites. And so we'll get a lot of additional data, and you get 3,000 occultations per day from the cosmic satellites when they go up. And this is really just to overwhelm you, and it's not even all-inclusive. I did not include, if you just read this, there's a magnetometer network. This is not right. There should be over 1,000. There are over 1,000 magnetometers globally around the world. And we're going to have geostationary high-resolution ionospheric images in the near future in 2005. And some of the others I mentioned, and some of them I didn't. But you can see that there are a lot of data sites around the world. Now, if you're interested in doing specification and forecast modeling, you need to have the data in real time or near real time. If you're just interested in science, it doesn't have to be in real time or near real time. However, you have to have pretty high quality data, and more importantly, you have to have the uncertainty in all the data so that you can include that in your model. So if I summarize what the current status is with regard to data assimilation, large global databases are becoming available and are already available. Sophisticated physics-based models exist. High-speed, inexpensive computer clusters are available. And common filter and other data assimilation methods exist and are readily usable. And so, my contention is that aeronomy is ready for data assimilation. And I also can predict, okay, but remember I'm a theorist, I'm also predicting that when data assimilation really takes hold, we could have another major advance in aeronomy similar to what occurred during the IGY. So now, if data assimilation is available or possible in aeronomy, what's the philosophy? What philosophy do we want to use? Well, the meteorologists have been looking at data assimilation for the atmosphere, the tropospheric weather, for 50 years. Oceanographers for 20 years. So it would be prudent to see what they have done. And indeed, what they found out is the most accurate specification and forecast models are those that assimilate real-time or near real-time measurements into a physics-based model. They found that better predictions are obtained for the atmosphere and ocean when more measurements are used, which is kind of obvious, when there is a better geographical distribution of measurements, when there is a greater frequency of data ingestion, and when the data are assimilated with a rigorous mathematical approach like a Kalman filter. And they put a lot of effort in to prove this over the years. Now, have there been data assimilation attempts in space physics before? And the answer is yes. This is everyone is probably familiar with this one if you're in aeronomy. Assimilative mapping of ionospheric electrodynamics, Art Richmond and Comiti, and then JPL's global ionospheric maps. And then there are some other efforts. Now these are very good first steps in the right direction, but none of these do what the meteorologists and oceanographers do. They don't use physics-based common filter data assimilation models. So they're good first steps, but this project that I'm involved in, global assimilation of ionospheric measurements, it's the first step where we're actually trying to do what the meteorologists and oceanographers do, use a physics-based common filter data assimilation approach. There are two university consortia, one at Utah State University, one at the University of Southern California, and we work together on developing algorithms. And what is our approach? We use a common filter technique for the main assimilation algorithm, which continuously reconstructs the global electron density as a function of time. So once the approach gets going, the data come in real time. That's the theory. And the uncertainties in the data are associated with it, and there's a physics-based model, and you get a continuous reconstruction of the ionosphere from, as you'll see, from 90 kilometers all the way up to 30,000 kilometers, and it's done as a function of time. Now I'm going to give one example, and it's a physics-based common filter data assimilation example, and as I said, this is the approach used by the meteorologists and oceanographers. And in this case, we need a physics-based model. The one we're using is an ionosphere plasmasphere model I developed recently, and it has 6 different ions in, because we're going from 90 to 20,000 kilometers in this example, so we need H plus and HE plus. We're covering mid to low latitudes, minus 60 to 60 degrees latitude, 0 to 360 longitude. Now for this example, if you use real data, you have real problems. Okay, so that's a whole separate issue, and that presentation would take 5 hours. So I'm going to skip that. For this example, we use synthetic data. We take the ionosphere plasmasphere model, we change the wind field significantly, and then we run the ionospheric model. Then we pretend that we don't know what we did. So we have an ionospheric model run as a function of altitude, latitude, and longitude in time, and we don't know what it is. Okay, we just say, all right, we forgot how we got this. So, and we call that the truth. Now it's only a model result, so it's a lie. So we call it a true lie, like Schwarzenegger's movie. Okay, true lie. Okay, but we're going to call that the truth, meaning that's a weather simulation. Okay, some weather took place, we don't know what it is. What we then do is, we then probe that weather simulation. It's varying with time. We probe it the way real instruments probe the real ionosphere. And we get TEC along rate paths. We get bottom side profiles. And we probe it. And we put the sites where the real sites are. And then we add noise to it because the real data are noisy. And then we just take the data. And we take the ionosphere plasmasphere model. and we use a common filter, and we try to reconstruct the electron density profile to see if we get the right answer. So that's the philosophy behind this example. And we needed synthetic data, but we took the real geometry of instruments. So we have 100 ground-based GPS stations. That's the JPL network. We took those locations, and we took the proper locations for the GPS satellites, but we cut through our model result. We have 16 digisons, and those are the ones in the Air Force network. We get bottom-side profiles. We took 2 polar orbiting satellites, and then the future CNOF satellite, which is going to be an equatorial satellite. It hasn't been launched, but that doesn't stop theorists. We put the CNOF satellite in there. And then we have, the point here is the data are assimilated exactly as they are taken. You don't change slant TEC to vertical. You don't do anything. You just take the data the way they are. Now here, if you look at the blue triangles, those are the 16 digisons. Okay, so this is a map of the Earth, and those are 16 digisons. The red dots are the ground-based receivers, GPS receivers, and there are 100 of those, and they link to the GPS satellites, and the links are shown along these curves. In 1 hour, this is what the link is, because the Earth rotates, and therefore the link moves. And then these are the 2 polar orbiting DMSB satellites, and this is the CNOF satellite. So we took real geometries, and we're going through this weather simulation, and we're producing synthetic data with noise. And of course, as time goes on, the Earth is rotating, all these positions move. Now, the fact that all of this moves is automatically taken into the common filter. And if one of the links goes off, or if one of the ionosons don't work, that's automatically taken into account into the common filter. Now, this is just an example of a common filter result, and I'm not going to go into a lot of detail. There's a data assimilation session Tuesday afternoon, and Lutke Shearless in our group will talk about this simulation in more detail. But this is from -60 to 60 geographic latitude and 0 to 360 longitude. And this is, the magnetic equator is off the geographic equator. They're not aligned. That's important to get the right geometry in this. And this is what we call the truth, the true lie. It's the weather simulation that we did with the model that we pretend, it's just a real event. And what we've done here is it's a 3D model. It goes from 90 kilometers to 20,000. We integrate vertically upward to get vertical total electron content. And that's what's shown here as a map. This is a snapshot at a given instant of time. The red corresponds to high TEC, and these are the Appleton Peaks near the magnetic equator. And the blue corresponds to low TEC, and the dark blue here means we didn't run the model that far. See, we didn't run the high latitude domain for this particular simulation. The middle panel is the common filter reconstruction. We take all those data that we talked about from the different sources, we add the noise, we put it in a common filter, use the physics-based model, and try to reconstruct the top. Now, the bottom panel shows the difference not between these two. It shows, suppose you had no data and you just ran the model, okay? And you just use time-dependent empirical models like the horizontal wind model, and you ran that. That we call climatology. So the bottom panel shows the difference between the common filter reconstruction and climatology if you had no data. So if you're green, that means you're just reproducing climatology. You have no measurements in those locations, so you can't improve upon it. If you're red, that means the data helped you get above the climatology and close to the right answer. And if you're blue, that means you went below the climatology result to get the right answer because of the data. And so I'm going to just show a little quick movie of this. We did a two-day simulation for this particular event, and as time goes on, you can see wherever these pluses just show the ground-based GPS sites, but you also have satellites going through there, as I indicated, and you got the ionosons, but they're not on here. But you can see wherever you have data, you're getting an improvement, and you're actually reproducing the weather simulation. And when you don't have data, you go green, meaning you're just going back to climatology because you have no information to tell you what the real world is doing. So this is consistent with the more data you have, the more likely you're going to get the right answer. But the technique really works, and it actually works better than I originally anticipated it would. So this is 2 days, and you're getting a snapshot every 15 minutes. So we could go get coffee while it finishes, or I could just move on. So let me just move on. Now, when the model is complete, we got a 5-year program. We're at year 3.5 through the 5-year program. What will a model produce? Okay, there's a continuous reconstruction of the global electron density distribution throughout the ionosphere and plasmasphere, and we're currently moving to high latitudes, so there'll be also the high latitude ionosphere and polar wind. So we'll go globally from 90 to 30,000 kilometers. And in addition to getting the electron density in this global grid, snapshots as a function of time every 15 minutes, day after day after day, we're going to get, of course, a whole bunch of auxiliary parameters, the height of the F2 layer, the density at the F2 peak, the height of the E region layer, the density at the peak. We can get slant and vertical TEC. You can get a whole bunch of other parameters. Also, we get the model drivers. In other words, the ionosphere is driven by winds and electric fields, and that also comes out of the common filter, because everything has to be self-consistent to get the right answer. So we'll get high latitude convection and precipitation patterns as a function of time. We'll get low latitude dynamo electric fields as a function of time, the global wind system, and neutral composition. Now, I didn't have time to go into it, but we're also doing a common filter for the neutral atmosphere. And Tim Fullerall and Mike Kodrescu and his group, they're working with us as part of the USU consortium to do a common filter data assimilation approach for the atmosphere. Now, if I conclude with regard to data assimilation, tens of millions of ionospheric measurements per day are already occurring. So this view graph I did this about 6 months ago. It's already old. I suspect within 10 years there'll be hundreds of millions of ionospheric measurements per day. And physics-based data assimilation models will provide real-time snapshots of the global ionosphere at regular time intervals, day after day after day, so you can see the dynamics within the ionosphere-thermosphere system closely. That'll provide information not only on the ionosphere and thermosphere, but you'll also be able to deduce what's going on in the magnetosphere. I predict that many outstanding scientific problems will be resolved once we have that tool available. And of course, there'll be numerous ionospheric applications that the applications community can use, space weather community. And if it works the way I envision, and to a large part, it's going to be dependent on the experimentalists getting the data quality and getting the uncertainties to us. So if my prediction doesn't work, I blame it on the experimentalists, which is a good position to be in. It's their fault that it didn't work. If it works, I'm predicting that we're going to have a major advance in astronomy comparable to what happened during the IGY. And for those of you in the field, I'll just leave this up there for you to read. But I think a lot of outstanding problems that have persisted, for decades, will be resolved once this data assimilation model is running routinely. Thank you. Sure. Can you see where it is?
Thank you very much for a delightful talk, Bob. And I also appreciate your sense of humor about so many things. The highest honor, the highest recognition that the sections can bestow is the Bowie Lectureship. And on behalf of the Executive Committee of the Space Physics and Astronomy section, and on behalf of the American Geophysical Union, I'd like to present to you a certificate that recognizes you as the 2002 Marcel Nicolet Lecturer for your lecture that you delivered today.
Thank you.
And now we'd like to open up the microphone for questions. Yes.
Well, I think a lot of people are starting to look at the issues, but I'm going to try to get an effort going whereby a lot of people will put the data on the web in real time and put real uncertainties associated with the data so that we could just pull them off the web in either real time or near real time for it. But there has to be a major effort by the experimentalists to make this data readily available and to get it in the form that we need. And so, but I noticed even in the last 3.5 years, John, that a lot of people have started to look at this and started to put their data on the web. And I guess just yesterday, Mark Hairston told me that all of the DMSP F-13 satellite data will be on the web now. And so people are thinking along these lines, and I'm hoping that within 10 years there'll be a heck of a lot of data for us to use.
Question over here.
The other technologies have one or several of large, at least in Europe, with no forecast. It's obvious that every once in a while, the two models around there are naturally with the forecast. When I left, one was predicting in the winter, a couple of Europe within a few days, and the other one was saying, no, it's going to happen. It's not happening. To what extent are just very similar problems around here, so the knowledge and they don't really need this.
Right. Right now, fortunately, we're the only ones doing this, so I don't anticipate a problem. But the minute the second model becomes available, and we do actually have a couple of competing models within our own consortia that we're comparing, this is a real problem. We've already saw that you can use two different models and take in the same data and get different results. And it has to do with what the uncertainty is that you will give to the data. The experimentalists haven't given us uncertainties, so theorists are coming up with uncertainties for the data. And that's what I blame as the real problem. But then the models are also uncertain, and what you pick for the uncertainty for the models also comes into play. So I think Vitenis mentioned a very important fact that we're going to have to worry about getting different results using the same data in different models or the same models and different data. But that's one of the things we're going to have to learn, and I'm sure we're going to have differences. You know, it's not going to be a perfect system for a while.
This is the well-established Siegel's law that a person with one watch knows what time it is. A person with two watches isn't sure.
Right. But right now, there's only one model. So, you know, I hope nobody else develops one.
Oh, yeah. Okay. Well, let's see.
I actually interested in a lot of things in meteorology community, the atmospheric community, and you're talking about phenomena of the atmosphere, models, and so on. I would like you to, first of all, I appreciate the lecture. I greatly enjoyed it.
Thank you.
And I wonder if you could sort of clarify the relationship between the model and the science. What is the scenario? I had this discussion yesterday with meteorologists and such. And, you know, if you give a scenario, say, how do you believe this model can scientists understand it?
Well, I think part of the problem we have is that we never have the data in the place where you want it. Now, if you have a lot of data that you can assimilate into a model, the model will then, through the physics, fill in gaps, okay, and fill in missing regions and missing time domains. Now, the real difficulty is if the physics-based model doesn't properly describe the physics, then you're going to get an erroneous result. So that has to be folded in as part of the uncertainty in the model. For example, the model we're using does not rigorously take into account the excitation of plasma instabilities and the formation of equatorial bubbles. So if we're assimilating data in a region where there are equatorial bubbles and we don't know they exist, we'll just get a huge density depression, and we'll say that's due to some unusually large wind or some really strange electric field. And so you got to be aware of when the model is weak and when the data are weak. And there's no really short answer I can give you. We're just going to have to be doing a lot of learning over the next few years. But we're aware of the possible problems.
Questions out there?
You concentrated on the response to the ionosphere. If you look at the comments of the versus drivers, the solar input, the oral input.
Oh, they are very important too. I just didn't have enough time to go into all the details. But all of it has to be self-consistent. We have to get the EUV, the extreme ultraviolet radiation, correct. We have to get the winds right. You have to get the electric fields right. And in addition to having electron density measurements, we will be using satellite measurements of particle precipitation and satellite measurements of drifts directly in the Kalman filter to help get those inputs right. So if we do it all correct, everything should be self-consistent and everything should work out. In other words, the drifts will agree with the satellite measurements or the Superdon radar measurements, and then the particle precipitation will agree with the measurements on satellites that are measuring the particles, and then the electron densities will all come out right. It's a big task, similar to the meteorologists and the oceanographers, what they had to encounter. And it's a lot of effort, but all of that is going to be included. I just did not have time to go into the details. Now, you get some more detail tomorrow afternoon in the data assimilation session.
question.
I think one of the first interesting experiments you can do would be to determine the decimal time that the weather people decide 7 days for within the certainty of within the uncertainty of the data at a given time run realization of different sets of official conditions to find out where they
In fact, that's what we're going to do for the forecasting. We're going to do an ensemble Kalman filter where you run an ensemble of states forward in time. You run a mean state which you think is the right one, then you vary all the drivers, and then systematically, and you project 20 states forward in time, a mean state and a bunch of others. So you not only have a forecast, but you'll have an uncertainty associated with the forecast. And we're also looking into that and doing that. But again, I just didn't have time to go into it. But I'm glad you brought it up.
A couple of questions here. Jack.
Bob, once you've got this density model, it seems like it's very easy to get some connectivity.
Oh, yes, that's a... Yes, in fact, we are. I didn't have time to go into the high latitude domains, but we have an ionosphere polar wind model that goes from 90 kilometers all the way up to 20,000 or 30,000. We haven't decided where to cut it off. But height integrated conductivities or just real conductivities as a function of altitude are one of the what I call auxiliary parameters that we get out automatically. And eventually we'll get horizontal and field line currents out in some of our electrodynamic modeling. That'll be part of it, but that's further down the road.
Mike?
Virtually all of the data for the assimilation is plasma data, or our plasma data, appropriate for an ionospheric model. But of course, the physics starts with the neutral atmosphere, and many of the chemical reactions of the fusion rate and fusion coefficient are related to the neutral atmosphere composition and profile. Do you see any future data sources, or is that the biggest need that you might have for data sources that will ultimately limit the model, inability to sample the neutral atmosphere?
Well, one of the drivers is there are two ways to look at this. We do have a common filter that Tim Fullerell and Kodreski are doing, and they're using UV satellite data in order to get the neutral atmospheric parameters. So we're having a separate common filter effort to get out neutral atmospheric parameters. But the other way to get it is, in order to get the right ionosphere, you've got to have the right neutral atmospheric parameters as well. So we have another approach whereby we're adjusting the neutral atmosphere and winds to be consistent with any wind measurements we have, as well as to be consistent with the ionosphere. So again, the whole package has to work to get the right answer. But we are separately looking into UV sensors. And in the year 2005, there should be a UV imager up there that's going to image the ionosphere, and we're going to get more UV data for the neutral atmosphere as well. And Tim Fullerell's already conducted some simulations bringing in UV data, the synthetic UV data, to try to develop an atmospheric model.
One or two more questions.
Following up on that question, well, we have a wish list of measurements we might see from space and like using measurements of light from the kind of measurements we had 15 years ago.
The more measurements we have and the more types of measurements we have, the better the model will be. I think the biggest problem is what Mike Mandillo said, is getting measurements in the neutral atmosphere. If we could get Fabry-Perot wind measurements around the globe, if we can get UV measurements to get out information on the neutral atmospheric parameters, that's probably the most critical at this point, because we have the least number of measurements concerning that. We got quite a few ionospheric measurements and electric field measurements and particle precipitation measurements, but direct measurements of the atmosphere we're kind of weak in.
Is the Kalman filter kind of the last word in frameworks, or are there new things in the offing?
Oh no, there are a lot of new things that are much more complicated, and part of the consortium is looking at more advanced algorithms for assimilating data, but that's more theoretical, and there's a pure mathematician doing that. And whenever he gives his presentation, it's wall-to-wall equations from one view graph to the next. So, I mean, I didn't want to get into that topic. But there are advanced techniques that can be used that are much more difficult to apply, but we haven't really pursued it from the practical point of view.
Okay, well, let's thank Bob again for an outstanding talk.